So we had Lenz's law. Lenz's law tells us the direction of the induced current, tells us which way the charges are moving. And it does so with the mantra, nature abhors, absolutely despises a change in flux. We also want to care about the magnitude of the current or the induced electromotive force. And that's given by Faraday's law. So Faraday's law says this. If I want to know how much electromotive force is going into pushing the charges around, so you can think of this as the amount of voltage that's being used to create that current, it's going to be given as follows. The EMF is equal to minus the change in the flux divided by the change in the time. So nature abhors a change in flux, and to get rid of that change in flux, it's going to create this electromotive force, which will create a current that will create a magnetic field that will oppose the change in flux. The fact that you're going against the change in flux is why you have a minus sign here, because you're trying to make a magnetic field that cancels out any change in magnetic flux. The electromotive force is just going to be proportional to how big the change in the flux is. So if you have a bigger change in magnetic flux, you're going to have even more electromotive force. And if that change happens in a shorter amount of time, you're going to have a bigger electromotive force. So it depends on how fast the change in flux is happening. Again, this is known as Faraday's law, and it tells us how much electromotive force we're going to get. Basically, how much of an effective battery we're going to put into the circuit by creating a change in the magnetic flux. Let's do an example to see exactly how Lenz's law and Faraday's law can be applied in practice. Suppose we have some circuit, and there's some resistance to that circuit, and we've got a magnetic field pointing into the board. And we're going to say that the magnetic field B increases into the board by an amount 3 Tesla in a time of 1 second. So my magnetic field is increasing into the board. We want to know what's going to happen in that circuit. What's going to happen to the charges in that circuit? Where are they going to go? How fast are they going to go? So to do that, let me just make some room. Hopefully you've written down the change in B is 3 Tesla. And that happens in a time of 1 second. First thing I want to do is figure out what direction that current is moving. So we said the magnetic field is increasing into the board. Well, nature hates that. Nature doesn't like that change in flux, so it's going to try to create an induced magnetic field out of the board. And to do that, my magnetic field is pointing out. I need my current going around this way by the right-hand rule. So that's counterclockwise. So we know the direction. Half of the problem is done. The next thing I want to do is use Faraday's law to figure out how much electromotive force we actually have. So I'm going to plug some numbers in here. Suppose our resistance is 4 ohms, and suppose the area of the loop is 2 meters squared. And suppose that the magnetic field is passing straight through the loop. So that's going to be an angle of 0 degrees. So let's see. Let's just compute our change in flux. So let's see. That's going to be the change in the magnetic field times the area times the cosine of 0 degrees. So that's going to be 3 Tesla times the area, which is 2 meters squared. It's the area of the loop, times the cosine of 0 degrees. Cosine of 0 degrees is just 1, so the few go away. So we're going to be left with a magnetic flux of 6 Tesla meters squared. I'm just going to write that over here. The change in magnetic flux is 6 Tesla meters squared. So we have that. And we want to know what's the electromotive force pushing that current around the loop. So all I'm going to do, let's just take the magnitude of the electromotive force, which is going to be equal to the magnitude of the change in flux divided by the change in time. So that's 6 Tesla meters squared divided by the change in time. We said that was just 1 second. So my electromotive force is going to be 6 Tesla meters squared per second. And if you combine Tesla meters squared per second and work out the units, you'll find that that's just going to be equal to 6 volts. So I can write that over here. Give myself a little more room. The electromotive force is 6 volts. Now that's just like I put a 6-volt battery inside the circuit. So when I do that, look over here, it's like I have a 6-volt battery in this circuit pushing current around counterclockwise. Well, we know if I want to find the current, I can find the current using Ohm's law, that the voltage is the current times the resistance, which means the current is the drop in voltage divided by the resistance, which in this case is just the electromotive force created by the change in the flux. So that's going to be a 6-volt drop divided by the resistance, which we said was 4 ohms, which should give you 1.5 amperes of current. So that's how this works. You have a changing magnetic flux, in this case due to a changing magnetic field, but we said it could be due to changing the area of the loop or changing the angle that it comes in, that it passes through the loop. We've got a changing flux over some time. I can use that change in flux to compute an electromotive force. In this case, we're going to get 6 volts for our electromotive force. It's like I just put a 6-volt battery in my circuit, so I can just use Ohm's law to figure out the current passing through. Now, I should point out that this resistor could be any electrical load. So it could be that I just put a flashlight in here, light bulb. And in fact, this is a pretty common use for induction. If you've seen the sort of shake weight flashlights, all you do is as you have a magnet inside, you have a coil of wire. In some cases, you can even see the magnet in the coil. You shake up the magnet on the inside. You shake up the flashlight. The magnet jostles around on the inside, and as it does that, it creates a changing magnetic flux, which creates a current, and you use that to power your light bulb. There are many practical applications for induction. It turns out that many of our power generators, wind turbines, all of those are powered by induction. If you go over to Hoover Dam, what you see is giant wheels that are being turned, and what that's doing is creating a changing magnetic flux as the wheel turns around. Maybe it's pushing a magnet through some coils. That creates a changing magnetic flux, which creates an electromotive force, and you can use that to power your light bulbs or computers or whatever you happen to be working with. It's the same principle as the shaky flashlight that we'd mentioned before. It's just on a much larger scale, and we use this to generate electricity. And I have a simple demonstration of it here for you. This is a hand crank generator. It's basically got this little turny crank. Now you can imagine that the turny crank is, here it's going to be turned by me cranking it. However, it could be turned by the wind. So it could be, we put some turbine on here, and there's a little propeller that spins around, and as the propeller spins around, it's like I'm turning the crank on my wheel. Now, if I just turn off my lights here, hopefully you can see there's a hand crank here. I'm going to take that off screen. But if I just turn my hand crank here, you can see my light bulb start to turn on. All I'm doing here is I'm turning the crank around. You can imagine that there's some magnet on the inside that is creating a changing magnetic flux, and as that changing magnetic flux goes back and forth, getting bigger and smaller, we create electrical current in the circuit, induced electrical current by an induced EMF.